This is the video presentation of the University of Minnesota Twin Cities FlyUMA DBF team. Here you can see the 3-view and isometric drawing of the FlyUMA plane. Major features here, you can see that the wing chord is 12 inches and the wingspan is 5 feet. Here you can see the different components of our plane. And again, this is a breakdown of all the different components that exist in our plane. This slide is an overview of the sensor assembly. So our sensor has a diameter of 1.15 inches, a length of 6.5 inches, and a mass of 150 grams. It has 3 lights on each side of the sensor body so that it can be seen no matter how it is flying relative to the judges. The plane carries 2 containers that are 75 grams each when empty, and a fully loaded container or container substitute is 225 grams. The retraction and deployment system you can see in the right picture. It has a motor that is a 58 RPM 12 volt motor with a reduction ratio of 76.8 to 1, which provides good torque for reeling in the sensor. The system contains a tow cable that is 5 feet long. It has double-stranded 18-gauge copper wire. Here you can see the weight breakdown over the airplane. On the right you can see a breakdown by component of the mass of each component. And then on the left you can see the gross weight for each configuration of the aircraft. So when there is no sensor and no containers, and only the sensor deployment and retraction mechanism, that is 3.995 kilograms. With the sensor but without the containers is 4.145 kilograms. And with 2 shipping containers, and one of those being the simulated shipping container, the gross weight is 4.585 kilograms. For the propulsion system of our aircraft, there are 2 motors that are T motor 3520 550 kilovolt. These are powered by 2 Tatu 4500 milliamp 6S LiPo batteries. The motors are controlled by 2 T motor AT75A ESCs. The system itself is integrated in the main structural spar of the aircraft, as you can see in the picture here. This location puts the propeller blades right over the ailerons and flaps, giving them good airflow for controls. In the picture you can see the motors are connected by carbon fiber tubes and PLA plastic that's been 3D printed. It has a safety factor of greater than 10 in combined floating. For our controls architecture, the controller we're using is the FrSky Tyrannus controller. It sends signal to the X8R FrSky 2.4 GHz receiver. That sends information to the Pixhawk 4 Mini, which sends its information to the ESCs and then to the motors, as well as to the different servos powering the rudders, flaps, ailerons. For the wing structure of our plane, all components in the wing were designed to withstand 4 Gs of loading at a minimum. They were designed using MATLAB and ANSYS. It was determined that 2 carbon fiber spars would run the length of the wing. On testing, tip deflection was found to be less than 2 inches under maximum load, with a safety factor greater than 2 to failure. The propulsion system components also undergo high loading. They were designed and analyzed using ANSYS and were analyzed using real-world testing to ensure that they could survive the high loading from takeoff and landing. The right side of this slide shows a mission scoring breakdown that was made before designing the aircraft. It was decided to attempt to maximize Mission 3 scoring and minimize at the expense of Mission 2 scoring. This is the beginning of the demonstration portion of this video. So on the left you can see the real world plane that was built, and on the right you can see the 3-view and isometric drawing of the plane.
Good to go.
Hold on.
And this will be a normal takeoff. I'm not going for 20 feet on this one. I want to make sure it comes off straight.
Hold on. You good? Yep. We're good.
Hey.
Yes, and I think it's going to be more accurate.
30.
Okay.
31.
I just love how Austin's right behind. I love how Matt's just turning.
How are we doing on